Welcome everyone for what is our last seminar for this academic year. We are very happy to have Emi Nakamura, who's going to talk today about her new paper, Learning About the Long Run, and Richard Crump, who is going to be the discussant. The format is as usual. Emi, you'll have 40 minutes for your talk, after which we'll move to Richard for a discussion. And there are a couple of questions that people can write, and I'm happy to convey them to you during the seminar. But most of the questions are usually in our informal part, which is not recorded, and that's usually after 1 hour when we stop the recording. And without any further ado, Emi, the floor is yours. If you'd like to share your slides.
Yes, thank you. Okay, can you see them?
Yes.
Well, thank you very much for the invitation. It's great to be here virtually. This paper is joint with Leland Farmer and John Steinson, and it's called Learning About the Long Run. So as is well known, there are a lot of documented anomalies when it comes to forecasts and even professional forecasts, which is what we're going to be focusing on in this paper today. So let me start by talking about some of the anomalies that have been documented in the literature. And I'm going to, throughout this presentation, I'm going to be focusing on sort of two leading examples. One is interest rates. So in this table below, I'm going to be running some regressions with interest rate data. So that's the T-bill line, and GDP growth data. The interest rate data is from the Survey of Professional Forecasters, and the GDP growth forecasts are from the Congressional Budget Office. And the one thing to keep in mind in these tables is that for the interest rate data, the forecast horizons will be in quarters. And that's just because for the interest rates, you'll see some of the most interesting anomalies are at shorter horizons. For the GDP growth example, the forecast horizon is going to be in years. And again, that's just because for GDP growth, it's going to turn out that there's some very interesting anomalies at longer horizons. So let me start by talking about biases in professional forecasts. So on average, interest rate forecasts are somewhat, there's a negative bias, a slight negative bias at shorter horizons, and it grows at longer horizons. There's not really any evidence of biases, on the other hand, for GDP growth. Another forecast anomaly that's been documented widely in the literature is autocorrelation. So here we're just taking the forecast error and running a regression on the lagged forecast error. And the particular way we're doing this is the forecast at time t plus h as of time t. We're running a regression on the forecast at time t of time t at time t minus h. So these are non-overlapping. And you see that there's, again, for the interest rate case, there's evidence of autocorrelation in these forecast errors. So in other words, when people are wrong in one direction, they tend to be wrong again in the same direction in the future. So this is autocorrelated forecast errors. Again, in the GDP growth case, there are no statistically significant deviations here. A third set of regressions, which Mincer and Zarnowitz very sort of famously discussed in their early paper, is a regression where you run a regression of the actual outcome, so that's y here, on the forecast of that outcome at time t. So here this is y at time t minus t plus h on a forecast of time t plus h at time t. And so the idea is that, if you have, Bayesian conditional expectations here, then the coefficient on the expectation should be 1. Now, in fact, when you run these regressions for the interest rate case, the coefficient beta is actually fairly close, at least in sort of quantitative terms, to 1. It's not that far from 1. Now here, the stars are denoting statistically significant deviations from 1, not from 0. And you see that, in fact, there are some statistically significant deviations from 1, but I would say, quantitatively, we're not that far from 1. In contrast, when you look at the GDP growth forecasts, you see that particularly at the longer horizons, we're very far from 1. So 3 years out, in terms of the forecast, you actually see that when the forecast moves by 1%, the actual outcome in terms of GDP growth moves not at all. The coefficient is essentially 0. And at longer horizons, when the forecast moves by 1%, the GDP growth forecast actually falls. So it goes in the opposite direction. So this is sort of a very extreme deviation. In fact, I'm on a committee for the CBO, and one of the reasons that we first became interested in looking at this GDP growth forecasting data was because of the fact that we sort of noticed this anomaly in the data. A second set of anomalies that that you might not immediately think of as related to these survey professional forecasters anomalies is the literature on the term structure of interest rates. So this is a literature that's not typically discussed as part of the same literature, but I think some of you will probably see as intimately related. So Campbell and Schiller in particular emphasized two tests of the term structure of interest rates, of the expectation hypothesis of interest rates. And those are the ones that we're going to focus on. So in the first test, we have on the right-hand side, the yield spread between the yield on long-term bonds and the yield on short-term bonds. And on the left-hand side, we have sort of like an ex-post yield spread. And the intuition, and you can derive it using simple algebra, is that when the yield spread is higher, then this coefficient beta should be 1. So when the yield spread is, when long-term bonds are expected to yield, so when long-term bonds, according to the expectation hypothesis, are basically an average of expected future short-term interest rates. So when the long-term bond has a yield that's higher than the short-term bond, that's a time period when people sort of expect interest rates to be higher in the future. And of course, that's the type of time period we're in right now. So it's very familiar. And so according to that very simple theory of the term structure, you would expect this coefficient beta to be equal to 1. Now, there's a huge literature demonstrating that, in fact, these tests of the expectation hypothesis fail dramatically. So when you actually run this regression, you get a coefficient on this yield spread, which is not 1, but is actually closer to 0. And again, here the stars are denoting tests relative to a null hypothesis of 1, because that's the null hypothesis coming from the expectation hypothesis. And so you're getting these coefficients that are closer to 0 than this null hypothesis of 1 under the expectation hypothesis. So the second test that Campbell and Schiller emphasized is this one. So here, again, on the right-hand side, you have the term spread between the yield on long-term bonds and short-term bonds. And now on the left-hand side, you have the change in the yield on the long-term bond between time t and time t plus 1. So the intuition here is that when the yield on the long-term bond is above the yield on, on the short-term bond, then that's a time period. One intuition is that in order to equalize returns between the long-term bond and the short-term bond, in the next time period, the long bond is going to have to take a capital loss. And that means that the yield on the long bond is going to have to rise. And so again, you can show using simple algebra that this coefficient beta, according to the expectation hypothesis, is going to have to equal 1. Another intuition is that a time when the yield spread is elevated is a time period when you're expecting, again, short-term interest rates to rise. So in that case, as you move forward in time, these long-term yields are kind of averages of expected future short-term interest rates. As you move forward in time, you're going to be dropping a near-term interest rate, and the average over the future is going to be higher than the average, which is including this very near-term interest rate. So again, that's sort of an intuition for why you would have a positive coefficient here. But in any case, you can show using simple algebra that the coefficient here should be 1 under the expectation hypothesis. And here, in some sense, the test fails even more dramatically. Here you get a coefficient of -1 instead of 1. So a very big deviation, again, from the expectation hypothesis. So there's a lot of important work sort of motivated by these kinds of anomalies in the finance literature. There's an important stream of work which is focused on time-varying risk premia. A second set of potential explanations for these facts relates to deviations from full information rational expectations. And again, there's a long line of work sort of emphasizing these ideas, sort of starting with this Fruit paper, which makes the point that if you replace full information rational expectations with survey expectations, then you can ameliorate some of these deviations from the expectation hypothesis. And there've been, quite a lot of follow-up papers since then. So we're going to see how far we can get with this second approach, that is deviating from full information rational expectations. In the macro literature, the reaction to these anomalies in professional forecasts has been sort of twofold. A traditional reaction has been that the forecasters are irrational or inefficient. So this was sort of the emphasis of the original Mincer and Zarnowitz paper, and it's an idea that goes back to Benjamin Friedman, among others. A more recent sort of evolution of these ideas is a line of work by Bordallo, Ginaioli, Ma, and Schleifer, and others. A second type of interpretation of these facts is that they reflect information rigidity or information frictions. And there's sort of two, streams of that literature. On the one hand, there's the sticky information literature, which emphasizes the idea that the individuals making the forecasts might be looking at somewhat old information. People are not able to continuously update their information about everything. So that's sort of the sticky information literature. A second strand of the literature focuses on noisy information, and that's taking the view that perhaps people don't see exactly the correct information. In fact, they're getting a noisy signal, and they have to draw inference about the thing that they're truly interested in from this noisy signal. And these seem like completely plausible explanations for lots of facts, particularly when it comes to households and firms that are focused on a lot of other things than macro forecasting in their everyday lives. But they seem somewhat less plausible for professional forecasters. So at least in my experience interacting with professional forecasters, they know exactly what the current interest rate is, without any error. They know exactly what the Fed did at its last meeting. There's no confusion about when the Fed made its interest rate changes or things like that. And so that would be an argument why these directions are less plausible for professional forecasters than for households and firms. But nevertheless, even if one takes the view that professional forecasters have the correct data and that they know the most up-to-date data, full information rational expectations is still a very strong assumption. Why is that? Because it's still assuming that these forecasters know the correct model of the economy. And that is, in fact, a very strong assumption, because if you think about ourselves doing research, we don't feel like we're sure what the correct model is. So it's probably more realistic to assume that forecasters, just like researchers, are learning about the model that generates the data. And when you're learning about the model that generates the data, including the parameters, this can fundamentally change the dynamics of these tests of rational expectations. And in fact, it can lead standard rational expectations tests to fail. And again, this is a point that goes back all the way to Benjamin Friedman's early work on this topic. And there have been a number of papers that have sort of made this point in various ways, that parameter learning can fundamentally change the interpretation of these tests of rational expectations. So here's a nice quote, I think, from Anna Cieslak that sort of captures these sentiments. She says, "Ex post predictability of forecast errors does not imply that people make obvious mistakes that could be easily fixed in real time. Even when conducting a quasi-real-time estimation, an econometrician uses ex post knowledge of a statistical relationship that would have been much harder to uncover in real time." Now, given that there's this argument, this pretty strong argument, I would say, that full information rational expectations is a really strong assumption, why hasn't it been that everyone has gone in the direction of weakening this assumption? Well, I think one important factor is that these models with parameter learning are actually very difficult to solve. And in particular, it's difficult to solve models with parameter learning in settings where the model is somewhat complicated. And so most of the papers that I talked about before, which focused on these parameter learning ideas, also focused on it in the context of fairly simple models. But in these fairly simple models, which you could actually solve, then the learning tended to be very fast. And so there tended to be this sort of conclusion in the literature that this kind of learning wouldn't be able to explain deviations from these tests that occurred over long periods of time, say several decades, like the ones that I was emphasizing at the beginning of the presentation. There is some discussion of the idea that parameter breaks might sustain learning over longer periods of time. And the idea of, for example, a constant gain in least squares learning is often motivated by that type of an idea, that there might be parameter breaks. But for the most part, this has been sort of a more informal discussion of this idea. And so the question sort of remains whether Bayesian learning can quantitatively explain these kinds of forecasting anomalies over several decades. And that's what we're going to focus on trying to analyze. So at the same time that I think there have been, this evolution in terms of the learning literature, I think it's also been sort of realized that you really do need somewhat more complicated models to understand the term structure. In particular, in the case of the term structure, I think there's been a lot of movement toward models that have some form of shifting endpoints. So some way that you can recognize the idea that people seem to believe in changes in the long-term trajectory of where interest rates are heading in the long run, and that's important to incorporate into the model. And there's certainly the same type of idea when it comes to GDP forecasting. So if you think about the debates on secular stagnation, for example, it's all about the idea that people's views on where growth is going in the long run have been changing over time. And that's important to understand the data on forecasts. But then the challenge becomes that these types of more complicated models can be very hard to learn. They have more parameters, and they're parameters that relate to the long-term properties of the model, where the individuals in the model are not getting very much information from each data point. So at each point in time, you might be getting quite a bit of information about the high frequency behavior of the data. You're getting much less information about the low frequency behavior of the data. So these questions that we're, I think, debating every day in the news about, what are interest rates going to be in the long run? Are they going to stay this low? What is growth going to be in the long run? Is it going to stay low? Those types of questions, you don't have that much data to answer those questions. And so that's the intuition for why, when you incorporate this idea that there's a long-term component and a short-term component to the dynamics of many processes, you can come to the conclusion that learning can be very slow, because you can have different parameter configurations that could yield the same fit to high frequency behavior, but very different implications for low frequency behavior. So what we're going to do is we're going to consider these two different applications. I'm really going to only talk about the first one, to interest rates, but in our paper, we also consider the application to GDP growth. And then it's really going to be a very simple type of exercise conceptually. We're just going to consider fully Bayesian forecasters. We're going to endow them with an unobserved components model and some initial beliefs about the parameters. Then in every time period, we're going to give them, another data point, have them generate forecasts in real time, and then ask by running the same type of regressions that I showed you at the beginning of the presentation, whether the forecasts that are coming out of this Bayesian forecasting model display the same kinds of anomalies as the actual forecasts. And then the question is going to be, can we actually, match some of these anomalies using our model? And the result is going to be that, in fact, we can. A crucial thing will be that in this model, because of the unobserved component structure that I emphasized at the beginning, learning is going to be quite slow. And so the priors will matter. And an important question will be whether we can match these forecasting anomalies even while we're assuming reasonably dispersed initial beliefs. And so what reasonable means is, of course, going to be in the eye of the beholder. But we're going to argue that, in fact, you don't have to believe something crazy at the beginning of time here to end up with the beliefs that we actually can fit these anomalies in the data. So the interpretation we have is that learning can actually generate quite persistent forecasting anomalies. And in this sense, rational expectations can be quite misleading, even over long time periods when low frequency phenomena such as long-term change in the trajectory of interest rates or long-term change in the growth rate are important. Okay, so let me talk about the interest rate forecasting example. So the data are going to be very familiar. So T-bill interest rate data and zero coupon yield curve data from Yu and Wu, as well as the survey professional forecasters data that I was using at the beginning. So here's a picture that I imagine is familiar to all of you. The 3-month T-bill yield going back to the 1950s. So our analysis in terms of the learning model is going to start in 1951. So that's after the Treasury Accord, and that's because we believe that that was an important change in the regime of monetary policy. So that's when we're actually going to initialize, the learning model. People are going to start learning in 1951. On the other hand, all of the regressions I'm going to run, they're actually not going to use data until somewhat later because, for example, the survey professional forecasters data we have doesn't start until 1981. So there's in some sense going to be some burn-in element in our analysis. So here's a picture that I've sometimes heard referred to as the hare plot or the hairy caterpillar plot. It shows at each point in time the black line, the actual interest rate, and then the dots coming off of it are the forecasts at different horizons going into the future. And so you can see from this plot where some of these anomalies come from in the data. Because if you look at some of the easing cycles, like for example in 1990s, you can see that repeatedly as interest rates fell, forecasters just kept thinking things would go back to normal, and they just didn't. And the same thing happened, for example, in the early 2000s here, or here you see the Great Recession. There was sort of a similar type of phenomenon. Now you can also see some features that our model is definitely not going to fit. So here, after the Fed really does serious forward guidance, then the term structure just completely collapses to zero. And that's going to be an example of something that our model is not going to be able to fit because our agents in our model are only looking at past interest rates to form these forecasts going into the future. But this gives you a sense of, for example, why it would be that the forecast errors are autocorrelated, because you see that in these episodes, as the forecasters repeatedly believe that things are going back to normal, they're repeatedly making errors that are in the same direction. So here's our model. It's actually just a 3-parameter model. There's going to be a random walk and a transitory component for the interest rate. So the interest rate is the 3-month T-bill yield is Y, and then there's this random walk component mu, and then there's a transitory component X, which is an AR1. And the parameters are first there's gamma, which is the variance share of this permanent component, this random walk component here. Then there's rho, which is the AR1 coefficient here, the persistence of this transitory component. And finally, there's sigma, which is the conditional volatility of the short yield. And you can already sort of get a sense for what kinds of identification problems these forecasts are going to face, because it's going to be kind of complicated to tell the difference between a very persistent transitory component here, the X, could it be that it is really just transitory variation, but it has a very high rho on the one hand, or on the other hand, maybe you have a very high rho for the permanent component, mu. And those things are really going to look quite similar at short horizons. But when you're trying to make forecasts 10 years out, they're going to look very different. So that's kind of the type of example of an identification problem that the forecasters in our model will face. So as I said, conceptually what we're doing is going to be very, very simple. We're just going to feed these forecasters data, one data point at a time. At each point in time, they will estimate the model. They'll get a whole distribution of parameters and so on. And then they're going to forecast interest rates into the future. And we're going to use these forecasts to calculate long-term interest rates using the expectation hypothesis. So just calculating averages of the future short-term interest rate and applying the expectation hypothesis to come up with the predictions in this model based on the expectation hypothesis for the long-term interest rate. One shortcut that we're taking during the zero lower bound period, I think that the right way of modeling things would be to view the data as censored, but this would kind of force us to move away from our linear model in certain ways, and would be very costly from a computational standpoint. So we're going to use this shortcut of just turning off the parameter learning during the ZLB period. The reason for this is that if we don't do this, then because interest rates are not really moving during the ZLB period, the forecasters in the model conclude that the variances are really, really small, which of course doesn't seem like the right conclusion. So one thing that I'll show you is that in this model, learning will be very slow, and as a consequence, the initial beliefs of the forecasters will matter. And so an important question is going to be whether we can match the anomalies in the data while assuming reasonable initial beliefs for forecasters. And here, what I actually mean by reasonable is reasonably dispersed initial beliefs. Because if the results that I was going to show you were showing that we could match these anomalies, but it really required point mass priors on the parameters, then that would seem like not a very interesting result. And in fact, we're going to show that you can start with reasonably dispersed initial beliefs and still generate these anomalies that we see in the data. So how are we actually going to choose the initial beliefs? Well, we're going to choose them to fit the anomalies. So we're going to assume that there's some kind of hyperparameters for these initial beliefs. So the rho, this persistence of the transitory component, has a normal distribution with a mean and a variance, and the gamma has a beta distribution. So these distributions for the persistence of the transitory component and the fraction of variation that's associated with the permanent component, these are the distributions that we're going to search over, and we're going to ask the question, what has to be true about these initial beliefs to fit the anomalies that we actually see in the data. It turns out that the prior associated with sigma squared, the variance, is not very important in the results, so we just fix this. It's something that's highly dispersed. So in particular, we minimize the sum of the squared deviations between the model and the data regressions that I showed you at the beginning, these anomaly regressions. We've also tried various other ways of doing this, such as fitting the hair plot, but the fit is sufficiently good that for this application, it doesn't really matter how you fit the model to the data. So here, here's a picture just showing the data again, the hair plot, and this is the model generated data on expectations of interest rates at different horizons. You can see that we're capturing some of these salient features of the interest rate data, like the fact that I was emphasizing earlier that in the 1990s, repeatedly forecasters believe things are going back to normal and they just don't. Same thing happens also in this Great Recession period. And then there are also things we don't capture, like I was emphasizing here, in the actual data, at some point, interest rates just collapse to zero after the Fed does forward guidance. In our analysis, they never see this forward guidance, so that doesn't happen. But there are a number of these salient properties that we're capturing using our model. So now we can actually run these regressions. So we're going to run regressions for bias. We can basically capture the fact that there's a negative bias in the interest rate forecast data. Autocorrelation, we can also capture the fact that the forecast errors are autocorrelated The model is the second row here, the data is the first row here, and you see that we're able to basically match the results from the data here. The Minzer-Zarnowitz regression, remember this was actually fairly close to 1 for the interest rate case, but it's somewhat statistically significantly different from 1, particularly at the longer horizons. And again, that's something that we can capture in the model. And then another regression that recently people have been looking at using various forecast data is this regression that's been introduced by my colleague Eric Granochenko and Oli Quebian, where you run a regression of the forecast error on the change in the forecast. And the idea is that if this coefficient is positive, it says that you're updating your forecast upward, but you're actually still too low. The forecast error is still positive. And so that suggests that there's underreaction, in the sense that you should have updated your forecast more. And you can see that we're also fitting those facts in the data. Now for the term structure, the expectation hypothesis tests, remember that here, the first Campbell and Schiller regression, the prediction of the expectation hypothesis is that the coefficient on the yield spread would be 0 and would be 1, but in fact in the data it's closer to 0 than to 1, and that's also something that we can generate in our model. The second Campbell and Schiller regression, again the prediction of the expectation hypothesis that the coefficient would be 1, in the data turns out to be closer to -1, and that's again something that we're able to fit using our model. So I want to emphasize that we are, choosing the value of these priors to fit the regressions, so exactly the regressions I just showed you. But on the other hand, it's 4 parameters that we're choosing for these hyperparameters of these priors, and it's 29 targets, you can think of it. So one way of viewing this is this is sort of a large amount of data reduction. We're showing you if you do this one thing in terms of selecting people's initial beliefs in this way, then you can, in a unified way, explain a bunch of different facts about the behavior of interest rates. So what, in fact, are these initial beliefs that you need to achieve this data reduction? So here are the initial beliefs. So this is the prior for rho, the prior for gamma, and for sigma squared. And so, are these reasonable or not? That's sort of in the eye of the beholder, but they're reasonably dispersed in the sense that, the rho, which is the persistence of the transitory component of interest rates, puts weight on values that imply widely varying half-lives. So in that sense, a lot of variation in what you might be convinced to believe about the persistence of this transitory component, and also quite a bit of potential variation in the role of this permanent component. Now, what's kind of the intuition for what's going on here? Well, that becomes somewhat evident by looking at how the beliefs about rho and gamma are being updated over time. So here I'm showing you the posterior mean of rho and gamma over time, starting from the beginning of our sample here. And you can see that there's this upward trend in rho and gamma over time. And so I think the intuition we have for what's going on is that the initial beliefs based on these priors that I showed you imply beliefs about interest rates that are a little bit too transitory. And over the sample period, people are updating in the direction of believing in somewhat more persistence. And this is unreasonable. So again, that's kind of in the eye of the beholder. But one viewpoint is that if you think about the 1960s, 1970s, these were time periods where when forecasters were looking back in time, most of what they had seen in history had been time periods when the US and in fact many other countries had been on the gold standard, where there really had been much more stationarity in interest rates. And so perhaps from that perspective, it's not completely unreasonable that people would have been surprised by how big the permanent component in interest rates was over the next decades. And finally, these are the estimates for the state variable mu in our estimates here, both the filtered and the smoothed value for mu. And you can see this big hump in beliefs about the permanent component, around 1980. Okay, so as I said, I'm not really going to have time to talk about the real GDP growth forecasting example, but let me just say that we do something very similar. We use real-time data on output, and we use it to update a very similar model about growth expectations. And we use it to fit very similar facts. So this is the survey professional forecasters data. So this is, again, a similar sort of hair plot. There's actual growth, and then the lines coming off of it are survey professional forecasters data about growth expectations at different horizons. And they're sort of similar facts to the ones I showed you before, where, for example, during the recovery from the Great Recession, forecasters repeatedly think that growth is going to be, very rapid, kind of going to go back to normal, and in fact, it never happens. And so we use a very similar model to the one I discussed earlier in the interest rate case to try to understand these anomalies. But in fact, we sort of show that we're able to match a lot of these salient facts. But I'm short on time, so I'm actually going to skip the rest of that application and just move to talking a little bit about the intuition for what's going on in our model. So why is it that we are able to generate these anomalies out of a model where the forecasters really are completely rational? So we're turning off all the other potential factors that might be important, like behavioral frictions and other kind of motives that might generate these anomalies. So to do this, let me do some Monte Carlo simulations. So now I'm actually just going to be generating data from the interest rate model and then estimating using that generated data. So now we have complete control. We really know the model is not misspecified. And I'm going to ask in the context of this kind of Monte Carlo analysis, what can generate the type of results we find in the data? So here's the interest rate model that I showed you at the beginning. I'm going to do 3 simulations. In the first 2, I'm going to choose as the truth parameters that are similar to what we estimate actually at the end of our sample. But the initial beliefs, I'm going to do 2 different cases here. In the first case, I'm going to choose initial beliefs which have the same mode as the actual truth. So they're centered on the location of the truth, and in that sense, they're unbiased. So even this isn't rational expectations because people don't know the truth, but it turns out to be close enough to rational expectations, basically to get back all the rational expectations results. The second case is going to be a case where people believe that in much more transitory parameters that actually turn out to be true. And the final case will be that they believe in much more persistence. And so the basic finding is that the results I showed you arise in the case where there are these downward biased initial beliefs. So in the case of unbiased initial beliefs, we get back all the full information rational expectations results. So there are going to be no anomalies. In the downward biased initial beliefs case, then we get these anomalies that we see in the data. So this is the case where initially people believe that there's much more transience in the data than there actually is in the model. And they're updating in the direction of more persistence, like there is in reality, but it's just happening very slowly. And there we get autocorrelated forecast errors. If we have the opposite direction, that people start out with too persistent beliefs about the economy, then we actually get things going in the opposite direction. So there's negative autocorrelation in forecast errors. And the same thing for the rest of the results. This is the Quebian and Granochenko regressions. Again, for unbiased initial beliefs, we get back the full information rational expectations case. Downward biased initial beliefs, we get back basically what we see in the data. In the upward biased initial beliefs case, we get the opposite direction. And the same is for the term structure results, that the downward biased initial beliefs gives us sort of what we see in the data, regression coefficient close to 0. The upward biased initial beliefs gives us a coefficient that's way too high, 2.5, whereas the unbiased initial beliefs gives us about 1. So this is sort of generally what we find. Okay, so the very last thing I want to say what is the intuition for this? Well, in this model, the learning is very slow. So here I'm showing you a picture of, the truth about rho and the truth about gamma, and updating about rho and about gamma. And you can see here that in fact there is updating. Beliefs are moving in the right direction, but it's happening very slowly. So the x-axis here is showing you the date, going back to 1960. So even over multiple decades, people are just not learning very quickly. And particularly if you look at the end of the sample period, you're just not converging that rapidly to the truth. And there is an important role here for this unobserved components element. If we turn up uncertainty about the long run, then you learn much more quickly. So this dashed line is showing what happens for learning in the case where we turn off updating about gamma, which is this permanent component, and you just know that there's no gamma. In that case, you learn much more rapidly than in our baseline case where you have this uncertainty about the long run. And that is why we called the paper Learning About the Long Run, because ultimately in these applications, the fact that there is this long run component makes learning much more challenging and means that it's possible to deviate from full information rational expectations for much longer, even in this case where you have fully rational Bayesian forecasters. Okay, that's it.
Thank you, Emi. There is one, maybe we're a little bit short on time, so we will keep the questions for later. Richard, if you'd like to share your slides.
Absolutely, thank you. Can everybody see them?
Yes.
Excellent. So first and foremost, let me thank the organizers for giving me the opportunity to discuss this paper. Let me also say that the views expressed here are my own and not necessarily those of the Federal Reserve Bank of New York or the Federal Reserve System more generally. And also in compliance with the FOMC policy on external communications during blackout periods, I'll refrain from expressing any views or providing any analysis about current and prospective monetary policy issues. So I thought I would start off with just a brief outline of what I'll cover in my discussion. So I'll do sort of a short summary of the paper from my vantage point. I'll try and summarize what I view as the key contributions of the paper and also try and highlight the points that I'll revisit when I get to the comments and suggestions on the paper. As it turns out, I was planning to focus on the short-term interest rate application, so that aligns nicely with the presentation that you all saw. Next, I'll aim to place the paper in the context of the existing literature studying survey forecasts, and then, like I said, I'll end with some comments and suggestions for the authors that they hopefully find useful. So in my opinion, the key contributions of the paper are sort of threefold. The first is that the authors study the role of sort of real-time parameter uncertainty and its effect on forecasts in an unobserved components model with a transitory and permanent component. And then they link this mechanism, I think holistically is the nicest word, to just a variety of I'll put anomalies in quotes, to different results that have been identified in the literature. So they really run the gamut through all these different results on the behavior of short-term forecasts and also on the nominal term structure of interest rates. And then finally, that they show that if you use model implied expected short rates as a stand-in for the actual yields that we observe, then sort of the conventional yield-based tests of the expectations hypothesis tend to have very similar properties as if you had used the actual yields. So that's what I sort of view as the key contributions of the paper. So I'm just going to talk briefly about the paper first, and then I'll jump into the rest of the discussion. So, you know, I just want to talk a little bit about the unobserved components model because, you know, those that are very familiar with these models, this won't be surprising, but I just want to make sure everybody's on the same page. So, you know, we observe YT, but we don't observe XT and MUT. MUT is a univariate random walk. XT is a univariate autoregression, and rho is playing the role of deciding the degree of persistence of XT. We also make the assumption that XT and MUT are mutually independent. In the paper, they sort of reparameterize the innovation variances just in a more convenient way, but that's not what I'm going to focus my discussion on. So we don't need to talk too much about it. So I just want to make a few comments to gain intuition. this is sort of a deceptively simple model. Obviously, if we could observe xt and mu-t, we would just stack this as a bivariate system, and we would just estimate the parameters by a restrictive R1. So it would be, relatively straightforward in the normal toolkit that we're used to. But the problem is that they're not observable, and so we have to estimate them. And since they have different properties, then it's very important to do the decomposition accurately to make sure that the forecasts are going to be accurate. But this becomes especially challenging if rho is near 1, because if rho is near 1, then xt and mu-t are going to have very similar time series properties. And so trying to disentangle these two components using observed autocovariances of various different lags is going to be a very challenging prospect. Moreover, just as another special case to reinforce how tricky it is, if xt and mu-t are correlated, so if they're not identified, or rather, if they're not independent, then we can't even identify all the parameters in the model. So like I said, this is a deceptively simple model. We look at this as saying, well, there's 3 parameters, but in fact, there's more than 3 parameters, because we can think of the xt and the mu-t themselves as parameters that we need to estimate. So it is a very challenging model to estimate, especially with just data on yt. And so the approach in the paper is to consider a Bayesian agent with some initial priors set in the early 1950s. And once you grant them those initial priors, then they can update the estimates of the states and the parameters and construct forecasts, in sort of the natural ways. And there's 2 sources of uncertainty now. There's uncertainty about the decomposition, what's mu-t and what's xt, and then there's uncertainty about the model parameters. And those interact in complicated ways to map into the uncertainty about the forecast. As was discussed in the presentation, the prior distributions are chosen essentially by simulated minimum distance to match the regression coefficients from the different regressions that were already discussed. So using both the short horizon forecast from the SPF and also the full term structure of interest rates. You saw this graph already. I really just wanted to show the prior distribution for rho, because I'm going to talk a little bit about it later in my comments and suggestions. But rho is centered at 0.76, symmetrically here, and we'll talk about this a little bit more later. Okay, so with these choices of priors, the model produces quite similar regression coefficients as in all these battery of tests. So regressions of forecast errors on a constant, i.e. our forecast errors on average 0. Regressions of forecast errors on lagged forecast errors. Do we see predictability of forecast errors? The so-called Mincer and Zarnowitz regressions, the so-called Quebian Granochenko regressions, and then also these regression-based tests of the expectations hypothesis. And I put that in italics because these tests only use yield data. They don't use survey data, whereas the first 4 use the short-term forecast data from the SPF. Okay. So what I wanted to do next is talk a little bit about the existing literature and some of the relevant properties that have been established about professional survey forecasts. Just as with generations and generations of discussants before me, I'm going to concentrate this discussion of the extant literature on some of my own work in the area. So for the first thing that I want to note from the existing literature is that there's strong evidence that survey forecasts are made jointly, so jointly across variables, and are well characterized by a multivariate unobserved components model with a permanent and transitory component. That sounds quite general. I think you can just think of it as a multivariate random walk plus a var1. So Andrade, Crump, Eusebio Munch, 2016, studied the term structure disagreement of professional forecasters. So looking at the cross-sectional properties of professional forecasts. And this is figure 1 in their paper. And what figure 1 in the paper is showing is average disagreement for different forecast horizons. So as short as 1 quarter ahead and going out as long as on average 6 to 11 years in the future. And what they show is that the term structure is very differently shaped depending on the variable. So for the short-term interest rate, it's actually upward sloping. For output growth, it's actually downward sloping. And for inflation, it's approximately flat, maybe slightly downward sloping. So they considered these new stylized facts about the different shapes of the term structure of disagreement and try and look for data generating processes that could generate such properties. And so what the paper shows is there's really 2 ingredients that are needed in a model with information frictions to match these stylized facts. And the first is an unobserved components model with this transitory permanent decomposition. And the second is a multivariate data generating process. And the key is that just having one or just having two by itself is not enough to match the behavior of the term structure disagreement. So I took a few graphs from the paper. The key is really the green line. So that's the model without a time varying mean. So that's a model without the multivariate random walk. And you can see it fails dramatically at matching the structure of disagreement, whereas the unobserved components model that does have the multivariate random walk, which is in blue, matches the shapes quite well. We can also learn from mean forecasts. So in Crump, Munch 2018, and then Crump, Munch, and Preston 2021, they studied the term structure of mean forecasts. By mean forecast, I mean just, say the blue chip forecasters, there's about 40 forecasters. So you're taking the average forecast across those 40 forecasters at each point. And so what they do is they use the universe of professional survey forecasts in the US. So 9 different surveys over 600 variable horizon pairs. And what they show is that if you write down, again, this unobserved components model, a multivariate random walk with a var1, it fits this universe of survey forecasts tightly out to very long horizons, even greater than 11 years, because actually some recent surveys ask about longer run forecasts, so not even with a horizon, which is like almost aligns perfectly with the omega t, with the multivariate random walk concept. And so the other thing the authors show is that when you compare the univariate fit to the multivariate fit, you get very different properties. So what this is a scatter plot of the actual observed survey forecasts on one axis, and then the fitted from these unobserved components models. And what you can see is that the univariate model, sort of visually, and they also show formally, fails relative to the multivariate model, in this case, trivariate model. And I think that's not maybe completely surprising that we would think that short run interest rate forecasts would be tightly linked to forecasts for real GDP growth and forecasts of inflation. And that's essentially what this graph is showing. And you can produce hair charts from these fitted survey forecasts. And I think the hair charts are nice. These are the term structure of expectations going out to 10 years. And these are forwards as well, I should say, not averages. And the terminal rate here at 10 years is almost like that multivariate random walk component, though maybe not exactly. But the key is that what that drifting mean is doing is it's allowing for the low frequency adjustment to beliefs to be captured by the model. And then you see, the very, very long downward decline in long-term expectations of the short-term rate. Okay, the next point I want to make, that sort of an indirect evidence in favor of the permanent transitory decomposition being a very nice mechanism to describe survey forecasts, is that there's a strong link between short-run forecast errors and revisions to long-run forecasts. So in Crump, Munch, and Preston, they look at this relationship. The real key is in this equation here. And so if I let H be very large, so I'm trying to forecast Z very far in the future, then the revision of my forecast to Z very far in the future is going to be approximately affine in my forecast error. And this plot here is from the papers, is looking at nominal short rate forecast errors versus revisions to long run forecasts of the short rate. And you can see there's a very tight relationship just visually in the data. Okay. And then the last thing that I wanted to establish from the existing literature is that if we use survey-based forecasts and take them as sort of the truth, then the expectation hypothesis sort of fails dramatically to account for the behavior of yields, but primarily at medium and longer maturities. So in Crump, Munch 2018, what the paper does is use the fitted survey forecast. So use this multivariate unobserved components model to fit all the different survey data, and then construct survey-based term premium at all maturities, including very long maturities. And survey-based term premium are very easy to construct in this way, because you just take realized yields. So you have an n maturity bond at time t, and then you just subtract average expected short rates over the life of that bond. And that gives you that term premium. Is that the real term premium? Well, it depends on whether it represents the beliefs of the marginal agent in the market, but it's an object that we can study. And the key is that if you look at a variance decomposition, so look at the explained variation in observed yields coming from either average expected short rates or this survey-based term premium, you see that at the very short end, so look at I'm looking at a 1-year bond here, That expected average short rates are the primary driver. They're the dominant source of variation. There's not very much room for survey-based term premium. However, as you move across the maturity spectrum and you start to move to longer and longer forward maturities, you see that survey-based term premia play a larger role, and then they become the dominant source of variation. And this is true for both nominal and real bonds. And the key thing is it's not that long-term expectations aren't moving. It's not that they're constant, and that's what's driving this result. Instead, they're moving, but they're moving in ways that have little correlation with the actual yields. And that's what produces this result. That's why the variance decomposition looks the way it is. And you can sort of see it visually. You have to sort of add up the black line and the gray line. So what this is these are different forward rates, the decomposition of different forward rates into three objects: real average expected short rates, inflation expectations, and then the survey-based term premium. So you have to add the black and gray lines, but you can see if you do that these are not constant objects, they're moving around. And so that's the key. They're moving around, but they're not moving around in a way that's correlated with yield. So if the survey-based expectations are the true expectations, and the expectations hypothesis really fails dramatically. Okay. So I think that has sort of laid the foundation for my comments and suggestions on the paper. And so I'm gonna cover sort of three areas that I think there's some room for some interesting additional work. So the first one I'll focus on is the properties of the model implied forecast. So the question that sort of comes to mind is, how well did the model implied forecast actually fit the short horizon survey forecast? So we saw the charts, and the charts look very good, but it's a little hard to tell from just visual inspection of the charts. And how it fits, but also when does it fit better? When does it fit worse? There was some anecdotal evidence provided in the paper and also in the presentation that's very useful, but I think a little bit more, maybe zooming in on some case studies, zooming in on some particular episodes would be useful, just because, the Bayesian learning in the model is, very complicated. It's hard to get a feel for what these model implied forecasts actually, how they behave. The second thing that I think, to be honest, of my comments and suggestions, I think I think the most important one is, how did the model implied forecast compare to medium and long horizon survey forecasts? So we have a lot of data on this now. And we know from the permanent transitory decomposition that mu-t plays this key role. And in fact, as the horizon goes out, mu-t plays a bigger and bigger role. The accuracy of the decomposition has the biggest implications for long-run forecasts. And since longer-term forecasts are available from the SPF, from Blue Chip, from other surveys, those are direct comparisons that can be made. And so, how does the model match the dynamics and behavior of these long-run forecasts? And what's nice about this is it sort of provides an out-of-sample check, since these forecasts aren't used to choose the priors. And so it can be read sort of as a nice sort of external check. And then finally, what are the properties of the forecast distribution? So, if you think about uncertainty around the forecast, is it of sort of a reasonable magnitude? We saw the uncertainty around mu-t, and it was quite large, I think understandably so, but how does that map to the forecast of yt? How does it move over time? How does it co-move with features of the model or the actual data, like the level of interest rates? And then also in more recent surveys, respondents are asked for probabilistic assessments of different outcomes. So different intervals, like sort of histogram forecasts for, the short rate falling between 2 and 3%, 3 and 4%, and so on. And so that would be also another natural comparison. You can take the forecast distribution and see if it has, implied histograms that are comparable to what forecasters themselves report. The next topic I wanted to talk about was the choice of initial priors. So, the authors are completely transparent about this. The initial priors play a key role in generating the results. And so then, I think it would be useful for the reader to have additional supporting evidence in favor of the priors that are chosen. So the first question is starting in the early 1950s the best choice? So at least to my knowledge, the earliest survey data on interest rate forecasts come from the Goldsmith-Nagin survey. That starts in December 1969. The SPF data start in the 1980s. So it's sort of unlikely that these forecasters were active before the 1960s. So one question would be, are there reasonable, and I put reasonable in quotes also, priors starting at the end of 1969, say, that produce qualitatively similar results? And one advantage of that is starting later would allow for, a bit more pre-sample and calibration to assess the priors. And it also would, it would also then allow the authors to skip over some of the complications about structural changes that might have occurred in how monetary policy was implemented in the 50s and the 60s. Alternatively, another way I think to check the priors is, suppose I am an agent in the early 1950s and I'm thinking about formulating priors on this model. So I think the following conjecture is not unreasonable. So if I'm standing in 1951 Q2 and I'm looking back in time to formulate these priors, I'm probably going to skip over World War II because T-bill rates were pegged at 3/8%. Maybe I want to downweight the Great Depression as well, since that was an unprecedented economic downturn. So then what data could I use? Well, T-bills weren't issued until 1929. But before that, certificates of indebtedness were traded in the 1920s, and they were comparable short maturity instruments. And so this graph here is from Ken Garbade's book, Birth of a Market, which is an excellent book. And I've circled, you want the thin line here, don't worry about the thick line. And that's the yield on certificates of indebtedness. Now I'm just doing a little bit of eyeball econometrics. I don't have the data, but if I look at the behavior of the yields here, they don't have sort of the familiar high frequency movements that you might associate with a row centered, as low as 0.76. At least to my eye, it looks more like, I would assign more mass towards higher row values. But again, I'm just eyeballing this a little bit. I think this is the different directions that could be used to just convince the reader of the choice, the priors. And then last on the slow learning results. So, as was discussed in the presentation, learning is slow here because you have a very persistent AR1 and you have a unit root process, and that's a very difficult decomposition to make. As I presented, there's strong evidence already from the literature that forecasters make joint forecasts across variables. So the question is a univariate model the right setup to study forecast behavior? So suppose the true data generating process is multivariate. What would be the implications for the results? Which results would stick around? Which might be compromised? How could they be interpreted in such a circumstance? I think that would be additional useful information for the reader. So in conclusion, I think this is a really nice paper, like I said, holistically evaluating a lot of anomalous behavior that we observe with short-term survey forecasts and yields. It covers a lot of ground, and I'll be interested to see additional new results. Thank you.
Thank you, Richard. We do run a little bit out of time, but we have a couple of interesting questions from the audience. And Emi, I think it's a nice, I'm going to summarize them somewhat, but it would be, once you answer, I think it's a nice summary of the paper. So one question is in relation to interest rates. So do we view your story about basically learning about the model, right, about transitory and permanent components as alternative to time varying risk premium? And another question from another member of the audience is, I'm going to paraphrase it slightly. So in the context of forecast revisions, do we see your story as alternative to, let's say, I think you mentioned it in the beginning, to the story of the parameter instability? So you say breaks, but they don't have to be breaks. Maybe they just change slowly, or it might be even simpler than that. Maybe it's just the agents are really having such a small amount of data like we do in macro. Maybe there is a really big estimation error in these parameters. So maybe the true row is truly 0.9, but with that many quarters that I possibly have, I just can't get that number. Maybe all I get is 0.4. So basically it could be one of these stories. So do we view your story that you presented as alternative to all of that, or are they kind of incorporated in some way? So basically that's the question. I think that's kind of a nice summary of the.
So on the first question, clearly there are a lot of things that our model is not explaining about interest rate behavior. I mean, a lot of volatility and so on. So I think there's a lot of room for time varying risk premia to play a role as well. But it is true that there's a component of variation in the term premium, which this learning mechanism is explaining in our model. And I think, for that component, it is an alternative to time varying risk premia. On the second question, I think maybe there are two parts of it. So one part is just sort of narrowly, our model, we chose this model where there's a permanent and transitory component but the permanent component is, moving in every time period. It's a run and walk, as opposed to there being structural change where it's, fixed most of the time and changes at more infrequent intervals. And that wasn't, because we really thought one model was better than the other a priori, but we actually started with a model that had this kind of structural breaks, and it turned out that just as a matter of the data really preferred a model which had sort of continuous change as opposed to infrequent large changes. So that's how we ended up with the model that we use. There's a second question, which is whether it might make sense to consider a model that has breaks in the parameters like rho, gamma, and sigma. So those are the parameters that our forecasters are learning about. And there I'm very sympathetic. In particular, the term structure literature has often focused on analysis starting around 1990 because of the view, which I think is completely justified, that the Fed had, a very different monetary policy regime before the Volcker disinflation than after. And so, this is also linked to some of Richard's comments. In our model, people are learning only from past interest rate data. So for example, if there's a major regime change at the Fed, and people are not just learning from what they see about the interest rate, but they're also learning from, what they think about the institutional change at the Fed, what the Fed says, those kinds of things, new mandate in some sense, then that would be, different from what we're assuming in our model, where people are just learning from past interest rates. So one of the things we do in our paper that is aimed partly at addressing this kind of issue is to consider a model which has a break in the parameters in 1990. Again, this is a little bit related to one of Richard's comments. And there we're kind of giving people a new prior as of 1990. And the idea being that people recognize that something important has changed at the Fed. And we actually do find that version where we allow for a break does fit some facts, in particular, a number of asset pricing facts related to the term spread and some other facts related to predictability of returns on bonds, such as the Cochrane and Piazzesi facts and so on, better than the model that doesn't allow for this break. So I think moving in that direction makes a lot of sense as well.
Thank you, Emi. So we're a little bit over time. So thank you, Emi and Richard, for the great talk and discussion. With that, we will stop our recording, and we invite everyone to our informal discussion, which is not recorded. And with that, we actually conclude the seminar series for this academic year. So we are going to resume in the fall.